Thank you very much. So let me outline the topic of my talk. The purpose is to formulate a new quantization principle for quantum field theory, which is based on a particular type of non-time ordered product. And I will show you that this is a principle that gives the ordinary theories of particles, plus another possibility, the possibility to include so-called purely virtual particles. What are these? They are sort of fake degrees of freedom, things that cannot exist on shell, that cannot be observed in our detectors. And how to obtain them? Basically, you remove every on-shell contributions to the amplitudes from these kind of particles, after showing that it is consistent to do so. But there is a price to pay. There is a gain. A gain is that you can remove ghosts, for example, and turn them into purely virtual particles and propose a solution to the problem of quantum gravity. And the price is that you have to renounce the idea that time is meaningful at arbitrarily small intervals, which is a price that many people are willing to pay for gravity. So the diagrams of the physical amplitude, the S matrix will be 1 plus IT. So normally you have the usual S matrix, and I will build another S matrix or another matrix T by means of the usual vertices and propagators, but also non-time ordered propagators. And so there is a certain map, a set of instructions to assemble the diagrams that we know of, to build the new diagrams into the new S matrix. And if the starting S matrix is unitary or pseudo-unitary, pseudo-unitary means that you have things like ghosts with negative kinetic terms, then the goal is to work out the map so that the new T obeys the unitarity equation in a certain subspace, which will be the physical subspace, where you remove what you want to remove. There is an arbitrariness in this most general solution, which is a certain anti-Hermitian matrix, and we will see how to fix it in order to break the time ordering, the violation of time ordering. So violate time ordering in a sort of minimal way, and this will give back the theories of purely virtual particles that I had introduced in a different, with a different approach earlier. And there is also an interesting application because besides being able to propose a theory for quantum gravity, you can also have from this approach some possibly detectable prediction for the tensor-to-scalar ratio, which is in this range. And if the precision will be increased enough in the next 5-10 years, maybe we will be able to. I will talk about that later. So about these purely virtual particles, what are they? And there are three formulations that I've proposed so far. So basically, it's like saying that normally quanta can be, or particles can be on shell or off shell, and these can only be off shell. Just take it as a general problem. How can I define something consistently that can only be off shell? Something that despises macroscopic detectors, and anywhere they feel that there is a detector, they avoid it. Kind of. So the first formulation was to start from the usual quantum field theory with normal particles and possibly ghosts, and start from the Euclidean version, and then you perform the Wick rotation in a different way, non-analytic, because when you reach Minkowski, you have to do something unusual. And this was proposed as a reformulation of the Leavick models. Basically, it's like averaging two analytic continuations. Instead of doing the usual analytic continuations around cuts, branch cuts, you average two analytic continuations, the two. And soon it was realized that you don't need Leavik, and actually this gives something different from the so-called Leavik models in purpose and also in the way it is formulated. And it can be used also for removing particle, a physical particle, if you don't want it to be visible. So let's say you want to build a theory beyond the standard model, you want to add some degrees of freedom that exist. They mediate interactions, but they cannot be observed. For example, what about the Higgs boson? Is it a true boson? Is it observable? Or is it just a mediator? What about the muon? The muon is observable because we observe it. But when you talk about resonances, Z boson, W's, Higgs, well, we never saw them really, and so this is a relevant question. Then the second formulation came last year, where we made an analysis of Feynman diagrams, and I will discuss this because the third formulation, the one I will talk about, is, I hope, much clearer, and it matches the previous one and the first one. And it's basically like an exercise on matrices. You start from a wrong S matrix. Let's say, what is the old quantization principle? You start from a classical Lagrangian. You separate the free part from the interaction part, and then you quantize it. It's usually produce an S matrix according to a certain formula. And the time order product is of key importance for that. But the point is that not always this S matrix is unitary, because unitarity doesn't follow automatically from the quantization principle. For example, if you have free fields with negative kinetic terms, which can come from higher derivative theories, then the S matrix you build with the rules I told you before does not satisfy the unitarity equation, but which can be written this way, when you separate the S matrix into the trivial part plus IT. But you have an identity like this one, where you have here a matrix which has, after diagonalization and normalization, is diagonal, but has not only plus ones in the diagonal, but also minus ones. Possibly zeros, but these are auxiliary fields that you can get rid of. So it's important to know that you can have plus or minus one, and you would like not to have minus ones, otherwise you cannot have that. So the idea is to obtain the good S matrix in a subspace. And normally you're stuck there. For example, for gravity, the problem arises because renormalizability can be obtained by adding higher derivative terms, but then, like these, you are in trouble with unitarity. So the goal is to start from the identity that is wrong physically, not acceptable, but is mathematically valid identity, and project it. What's the problem here in the projection? If you put some in and out states, just to be more explicit, you can certainly ignore from your sets of in and out states the unwanted things you want to ignore. But what's important is the product here. Here there is a product, and in this product, what appears, appears. You cannot decide what is inside. So you should be able to prove that if you remove something bad from in and out, automatically it disappears in the middle. And there are examples of this. Normally, we know of the most important example where this happens is due to gauge symmetries. And the gauge symmetry tells you, it guides you through this projection. So you have Takahashi, Slavnov, Taylor identities for the type of ghosts. And you know that if you remove the ghosts and the unphysical components of gauge fields from in and out, automatically they disappear inside. And if they disappear there, then it means that in a subspace that you call the physical one, you have unitarity. Now the question is, what if we do not have asymmetry that helps us? We need to change the inside of every diagram now. We need to change the definition of diagram, because otherwise we are stuck with that identity. And so the idea is this. You do everything as usual. When you get to your S matrix, if it is okay, maybe you stop there. Or if it is not okay, or even if it is okay, and you want to get rid of something just because you want to explore new frontiers, possibilities, you ask yourself, what other S matrices can I build out of it? So is it possible to make a further step in the quantization procedure and build a scattering matrix that is physical, by which I mean that is unitary in a subspace, out of the one that is not? And so you need a sort of reduction or projection, and we'll see in a moment what to do. For convenience, let me write S equal to 1 plus V instead of IT to save various I's in the formulas. And I will call V amplitude, even if it is a matrix. And so we want to build a unitary V from a pseudo-unitary one. And this is an exercise with matrices, basically. So you have a matrix V that satisfies an identity that is not a good one. Let's say because you do not have this on the right-hand side, you have anything you want with two Hermitian matrices A and B, Y2. Normally it's the matrix C that I wrote before, but I divided into A and B to say that A is the good one and B is the bad one. I want to get rid of one of the two and keep the other one. But for the moment, it's just an exercise of matrices. So you don't even know what physics is behind this, what is good, what is bad, just an exercise. So assume that you have a V that satisfies an identity like this. What is the most general reduced V that satisfies an identity like that? You get rid of B, of the wrong thing. Well, you can find the most general solution. The most general solution is given in this formula. So there is a very simple solution that you find right away. And it would be very nice if the answer would be just that. So you remove B if you take as your amplitude V this. Very simple geometric series. And this -1, we expand in powers of V. V collects the diagrams, the usual Feynman diagrams. B is just a diagonal matrix with some zeros and ones and -1s. But there is an arbitrariness, and the arbitrariness is encoded into an anti-Hermitian matrix, omega, and the most general formula collects the certain piece that is written here in a complicated way because it has to fulfill the requirements that you need, but it's simpler than the formula suggests. So let's see, the talk will be to analyze this formula and see what diagrams we obtain and how to obtain the diagrams of the previous formulations that I will describe along with this, because there are several interesting features that... So the simplest solution is not the good one, and we will determine this omega. Unfortunately, it has to be determined step by step, diagram by diagram. But first, let me show you how to use the theorem, because so far this is just the thing that is mathematics. I don't even spend time to prove it. It's just a matter of sitting down and manipulate the formulas. But there is no physics. So you have this, you start from this, and then if you choose A to be the projector onto some physical subspace, the one you want, so it will be diagonal with only ones, zeros. And you write B equals C minus A. Then this identity that we saw earlier, this one, A is the projection, so you have this identity, okay? Just and the physical amplitude, which will be obtained by further projecting to the left and to the right, will satisfy the normal identity, and the projected S matrix will be the projector to the onto the physical subspace plus this, and it will satisfy this identity. It's important to solve a problem of matrices. Kind of looks simple because you say, we always talk about S matrix. It's just a matrix in the end. So physically, we will distinguish A and B, the good and the bad, from in terms of fields. We will have the set of fields. Big phi will be divided into small phi and chi. Chi's are the ones we want to get rid of for any reason we want. Not important now. And the physical subspace, W, H, will be made of the states where any number of creation operators act on the vacuum. Okay, so the good ones, creation operators on the vacuum. That is the physical subspace. Only creation operators from the good fields. Instead, the complementary subspace is made of states where at least one bad creation operator acts on the vacuum. So at least one. So here only physical, vacuum, only physical, and here vacuum, at least one, which will be called purely virtual, at least one. So diagrammatically, okay, we'll see the diagrams what they are. Let's start from the propagators, and the good fields will have the usual propagator. The bad fields will have possibly some ghosts. There will be in the bad ones, or the ones we want to get rid of for any reason we like. So even we could get rid of a good one just because we think that it's unobservable for some reason. And well, you see in the formula that we saw earlier, there is an expansion here. For example, this is V minus 1 divided by 2 VBV, etc. What is this product? VBV, VB, VBV, etc. What is it? A product. It's just a product. That's the crucial difference. It's not a time-ordered product. It's a product. So if you have a field from one V to the left and a field from the other V to the right, left is left and right is right, and when you calculate them on vacuum, you have the Wightman function, not the Feynman propagator, the Wightman propagator, which, by the way, coincides with the so-called cut propagators of the Katkowski-Veltman identities that are used precisely to study unitarity. So basically, in the formula, you will not have just the usual diagram, but a collection of other diagrams that are made by gluing the usual diagrams, sub-diagrams from the usual, through different propagators, cut propagators. And you can have V, B, V, B, V, any number of B's you want. So any number of cuts you want. This will be in, out, and then according to the previous form, you have to take those diagrams and glue them together like this, build new diagrams, and let's see what comes out of this. because we still don't know. But here is it. For example, the truncated formula that we will need is just made of these few terms, including the omega. You see omega and v appear on the equal footing. Omega is the arbitrariness, v is your amplitude. V starts with the usual vertices. So with omega, you could even change your theory at will. For example, if you want to do jump from phi to the fourth to QED, phi to the fourth gives a v. You change omega, you change the vertices. You can jump from a theory to another theory just because this is mathematics with no physical inputs. So we will have to restrict this omega. It's not completely arbitrary. Omega will be determined in a way. Otherwise, we would not even know what theory we're talking about. So basically, omega at least should be of order v squared, not change v, not change the starting vertices. But apart from that, we still don't know order v squared, what it is. What are these products? They are just products. So instead of having time-ordered v contractions, you have v contractions, non-time ordered one. We will study omega equals 0, but let's see what happens, because it's kind of strange. Will not be so strange when you understand the meaning, but let's start from the simplest diagrams, what you would expect to be the simplest diagrams, the tree diagrams. Actually, they are not as simple as you might. So the simple propagator. Simple propagator is you have two fields, time-ordered product of two fields, and this is the usual amplitude, which I consider with sources, just a trick to see the field insertions as derivatives with respect to some sources, different sources for the same field, just to be redundant but as clear as possible. This is the usual propagator, but we do not want the usual propagator. We want, in the simplest formula, omega equals 0, something here, the usual propagator, here something else. What is this something else? Let's work it out. So instead of two derivatives of the usual amplitude, you take two derivatives of this amplitude, and you have the usual thing plus, you see 1 phi, b, 1 phi, 1 phi. These are non-time, b is 1 here. B is 1 minus the vacuum. So I will take, I will assume now that my physical subspace is just made of the vacuum. I want to project phi away. If I want to project phi away, then B is anything minus the vacuum. And what you find is the time-ordered propagator minus the two Wightman functions with 1/2 in the two orderings that you can obtain. And this takes out the on-shell part from the Feynman propagator, the two on-shell parts, and gives the principal value. So this so far is okay. It goes to the right direction because it removes the on-shell part. It looks like something that can define these purely virtual things. And this coincides with the propagator of purely virtual particles as I defined earlier, but it's not that you can use this propagator inside diagrams. Now we will see why. It's just a statement for the moment. But let's consider two propagators. It's a very simple diagram where let me see it's just two propagators. Three diagrams made of two propagators. You can have anything external attached to them, any sources, but so physically it could be particle, 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 particle. The important thing is that anything else is external. Internally, so you just have two propagators. Well, when you apply the formula, you see that you will have many contributions. They start to grow, where you cut in all possible ways. And this is kind of not so strange if you think that we are not drawing diagrams on the basis of the time ordering paradigm. Time ordering means that it doesn't matter if you draw the diagram like this or this. But if you don't have time ordering, it does matter. They are two different things. And so basically you have to decide what is earlier than what, and so on and so forth. And then the formula tells you, guides you through the thing. You calculate that. You use two fields now because you have two propagators and more sources. And you do the calculation, you find some surprise. And the surprise is that this diagram, which is just the product of two propagators after the projection, is not the product of the projected propagators we saw before. So let's call the projection of a single propagator P, principal value. You don't have just P1, P2. You have something annoying. And these deltas are made of on-shell paths that remain. So this is not the result that I gave in the definition of purely virtual particles. And but now here is where the omega correction comes to the rescue, because you can check that this thing can be removed if you fix that. Okay, and it is anti-Hermitian. You fix that and you remove it, and then you have this. Seems that you can do anything you want with this omega, but let's see, you cannot. And this was the case where you take two propagators and you want to project away both, because you want to consider both purely virtual. But you could say one field here is physical, P1, one field here is purely virtual, so this is physical. You have other combinations, then you would need to find the product of Feynman propagator times principal value. You can do that with the same correction. Then you can take three propagators. The number of diagrams starts to grow. This is just a vertex, non-amputated vertex with nothing. It's just three diagrams. So externally you can put up pairs that create anything you want. But the important thing is that what is internal is these three legs, or adjacent three legs. Then you can draw all the diagrams you want, and the truncation you need is like this. You calculate them all, and still you do not find, for example, if you want every leg to be purely virtual, you do not find the expected factorized result, you find something else. Okay, then you can correct it with the omega correction. If you have two purely virtual particles and one physical, things start to complicate a little bit, because you get this. This is the exact result you would like to find, two principal values and Feynman. Then there is something that you can remove like this by means of an omega correction, but there is also something else, and that you cannot remove. Why? Well, remember that the arbitrariness omega is anti-Hermitian, and here there is an I, but here there is no I. So one of the two, I have to check the I's, one of the two can be removed, the other one cannot. The one that can be removed is this one, and this one cannot. But now you remember that the formula doesn't stop by adding omega. There are omega corrections due to subdiagrams. Basically, if you have a purely virtual particle here, a purely virtual particle here, and a physical particle here, and you cut here with the physical cut A, you have a subdiagram, which is the one we saw earlier, and which needed already a correction, which was this one. So basically, once you go to complicated diagrams, you have an overall omega correction that sometimes rescues you and sometimes is enough, but you can use that only after having properly included the sub-corrections, the corrections from sub-diagrams. And then you get the result you want. And make the story short, this goes on. It's even more complicated than what I just said, because you can do it with 3 adjacent propagators. It's the same thing. You will find the expected result only after using this over omega, but also the omega correction into subdiagrams. Even worse, disconnected diagrams. If you take a diagram like a propagator and you multiply by nothing, a constant, still it's non-trivial. This is disconnected, you see. It's like take propagator multiplied by 2, 3, some number that you want to consider as a vertex with no legs, or another propagator, disconnected. What happens? Again, you do not find what you want. You find that you need a non-trivial correction for that, and even for subdiagrams. Product time 2 constants. Even if you take, for example, 2 propagators like this, disconnected, you expect the product again, but you find something else which can be absorbed in this omega correction, or overall omega corrections, and also due to subdiagrams. So this is the story of this formula. Now I go to one loop diagrams. They are simpler for some reason, because problems arise when you have factorizations and draw disconnected diagrams. One loop are simple. For example, we see the triangle, the box, very quickly other diagrams. And there is a way to simplify the analysis of loop diagrams for the purposes of unitarity that has not been noticed before, but is crucial. And it is to study the skeletons of those diagrams. You do not integrate on the space components of the loop momenta, but only on the loop energy. Only integrate on the loop energy. That's an algebraic operation by means of the residue theorem. Don't do anything more than that, because everything here is algebraic. You do not need to calculate any diagram. You will see tons of identities that have never been noticed before, and they make unitarity what it is. So basically, instead, and we multiply by 2 omega, you take the propagator and you divide it into 2 poles. E is the energy and omega is the frequency. Conjugate propagator is this, and the cut propagators, the Wightman ones, are just deltas. So there is a factor 2 omega that I introduced with respect to the usual propagators, but since I do not integrate on the space components of the loop momenta, this is a constant. Nothing. You do not integrate. Repeat this again, because otherwise it's very, very constant. So for example, if you have a one loop polygon, this is what you consider a product of propagators, but you only integrate on the energy. Then you have loop energy, frequencies, prescriptions. I put one energy for every one external energy for every internal leg. This is redundant, but makes the formula symmetric. So instead of putting external energies there, I put an external energy on the internal legs. This is more than what you need, but it simplifies the formulas. But when you do that, the triangle becomes very simple. Even the box, the pentagon, hexagon, they are just simple algebraic expressions that I show you. You need this crucial decomposition, but you do not have to use this before the integral on the loop energy, because otherwise it's a complication for nothing. You first integrate on the loop energies, then you use this on what you obtain later, and you will have a decomposition into principal values and deltas. So I just introduced some combinations of the basic quantities to see what's on shell and what's off shell. This is the idea. So this is the basic identity, but do not use it before integrating on the loop energy. Do not use it on this. because otherwise you will not see what's on shell and what's off shell. You have to use it after integrating on the loop energy. So, for example, if you take the bubble diagram and you integrate only on the loop energy, you will see that it decomposes into the sum of a certain principal value, two principal values, and two deltas. The two deltas are the usual cuts once you integrate on the loop space components of the loop. And you can easily see that if you use the formula before for the corrected amplitude, this one is sufficient. No omega corrections gives the correct result, removes the on-shell part, the delta functions, the threshold, and you get what you want. Double bubble is the same. Oh no, double bubble is not the same because it's a product. Because it's a product, you will not get the factorized result, but you get that plus corrections. But fortunately, you can remove them with omega. And you obtain the desired result. Triangle, since it is not factorized, it is simple. And this is the formula for the, it's as a skeleton, so integrate only on the loop energy. It can be written like this. This is the usual triangle with Feynman propagators. So 1 year ago, I analyzed how to decompose and organize the skeletons, and you find the purely virtual part plus some on-shell contributions. And the purely virtual part is a product of principal values with this formula. If you apply the projection, I think that here you need this, but you also need VB. I need to go to that. Here are the yes. Here you see two B's because you can cut twice. Then you automatically get the projection onto the purely virtual part with no omega, nothing. If you have some physical particles and some purely virtual ones, still you don't need omega corrections. The triangle is fine. If you go onto the box, you will find some more complications. We'll skip this. I want to talk about cosmology, but just to give you the idea, you can have fun with these formulas. You see that you will always match the results of the yes, the results that you need. Explain well. Right. So let me explain how I in this paper 1 year ago I defined the purely virtual particles. Basically, you take your diagram, in this case the triangle, you integrate on the loop energy only, and you find a long list of terms. You organize them into principal values and delta functions by the usual formula. This is the term with only principal values. This is the term with only deltas, one delta. This is the term with the product of two deltas. And then what is the projection? If you want some particle to be purely virtual, is the following thing. Let me write what delta IB was. These are the external energies, and then there are frequencies. So anytime you find a delta function where one of the frequencies of your fake particles enters, you drop it brutally. And then you get a new diagrammatics that satisfies the unitarity equation and that matches the formula that I am showing now by means of this non-time ordered product. So it's the obvious thing that you when you find this decomposition, the obvious thing you would do. And the match is, I find match with the new approach in all calculations, even more complicated diagrams, more loops, but skip this. And the two loops, the non-trivial diagram is the box with diagonal, which can be used for these corrections. And there is the box with a fake diagonal, like this, which can be used for this. You always find a complete match, but you need to use omegas now. So what we have learned. The projection, and when omega is equal to 0, is problematic because the product doesn't go into the product. But you can choose omega to find the factorized result. What omega should we choose for physics? Because any omega gives a unitary matrix. So the omega that I determined this way is the one that sort of minimizes the violation of time ordering, because it tells you that the violation is only in the prime factors, prime diagrams, like factorizing an integer number into prime factors, and only in the prime factors you can find the need of an omega. Okay, but still physics could be another one. So nature will determine what the physics is, but this is a privileged choice for diagrammatic aesthetical reasons. So why would the projection of a product be the product of the projections? I don't know now. Everything you can normally do with functional, generating functionals, go through only if you have this property. By the way. Skip this and define. Okay. Now let's see what you do for quantum gravity and how to get out of this the prediction for the tensor-to-scalar ratio. By the way, the prediction is this one. NS is the tilt of the scalar spectrum, which has been measured. Maybe it is written somewhere. Here. And R is the tensor-to-scalar ratio, the ratio between the amplitude of the tensor and scalar fluctuations. This is the Starobinsky limit, the Starobinsky prediction, which here is a upper limit. And this is the new thing. That comes from what? From applying these ideas to quantum gravity, which means that you take as quantum gravity the usual Einstein action, r squared, this is Starobinsky. R plus r squared with this sign doesn't have unitarity problems, but it's not renormalizable. And if you take those two, you get this prediction for R. If you want renormalizability, because why do I want renormalizability? Because I come from high energy physics, and I think that the principles that were so successful for the standard model should be equally successful a little bit further. So that's my choice. I want renormalizable theory, but this is non-unitary if, due to the y-squared term, if you don't do something. You quantize it as usual a la Feynman, or as with the usual Wick rotation from Euclidean, which is analytic and it is completely equivalent to Feynman, you will have a ghost. But if instead this is a purely virtual particle, it's a spin 2 massive, and the mass is this, then it will be a mediator, and you will not have it on the external states. But to make it this work with unitarity, you need to do what I told you before. Problem. What I told you before is from high energy physics. High energy physics is a flat space, Minkowski. Know nothing about background. Here there is a background. So here the problem has to be lifted to the problem of pure virtuality in a background, A of t, and that's the non-trivial part, which gives this bound, which would be totally non-perturbative from the point of view of high-energy physics. So you wouldn't be able to obtain it from high-energy physics only. So it's necessary to generalize the projection to curved space and ensure that what you do not want is not there at all energies. So what is lucky here and in cosmology in general, with or without purely virtual particles, is that although you have a non-trivial background, fortunately the problem is just a problem of for the spectra, harmonic oscillator in with time-dependent frequency, and you don't know how to treat it, quantize it properly. But fortunately, it becomes an ordinary oscillator with constant frequencies in two limits, superhorizon and subhorizon, and two different variables, by the way, because at subhorizon's case it's in conformal time, and superhorizon's case it's an oscillator with constant frequency in cosmological time. Well, those are the only two places where I can apply the ideas I told you before, because it's a just normal oscillator with constant frequency. And the bound comes from interpolating by demanding that the green function of this purely virtual thing in background tends to the two solutions that I already know for the two limits. So basically, see if I have this. No. So here you have to believe me a little bit, but I can give you more details if you ask questions on how this works. And basically, the reason is that at the tree level, because here we do not need loops for cosmology, we need tree diagrams, but in background, you have a principal value, but the principal value after Fourier transform in time is a sine of t times a coefficient here. And when you go to subhorizon limits, this coefficient is always the momentum, the space momentum, always okay. But when you interpolate to the opposite limit, it becomes the square root of mk minus something like that, which is real only if the inequality holds. Otherwise, you have a hyperbolic sign, which is not the green function for purely virtual particles. So why, in the end, am I saying that basically this idea of quantum gravity is completing but strengthening also Tarbinsky inflation? Because the prediction is very close to Tarbinsky, basically. Just check the numbers. Here are the basic, so this is the amplitude of the scalar spectrum, the amplitude of the tensor spectrum are to the leading order only. This is the scalar tilt, I called it NS previously, -1, this is the tensor tilt. And what are the Tarbinsky formulas? mk equal to infinity, because you kill the pi squared. And the prediction, which is maybe here, yes, is this, comes from this formula. So let me elaborate on that a little bit. So basically, if m chi is infinity, you get Starobinsky. But the point is that even if m chi is 10 times m phi, you will get Starobinsky. What I want to say is that the prediction is this interval, okay? You have this for m chi equal to infinity. You have this for m chi equal to the lower value, which is m phi divided by 4, and you know that m phi is 10 to the 13 GeV. But the formula is that even if m chi is not infinity, but just 10 times this, the result will be so close to the Starobinsky prediction that in the first run, we will not see any difference. So let's assume that my prediction is the right one. And the window is this, let's say. I have to hope to see a difference with respect to Starobinsky, that, and not only that m chi is in the window, but that m chi is very, very close to the lower bound. Because otherwise, take this ratio, 1/10. Let's say that m chi is 10 times m phi. This is 1 divided by 100. And so I will, this theory basically is saying that Starobinsky is right. And only in a long time, much later, we will see the difference. So I can conclude here. Thank you. So for example, if you do not treat this y squared as and this chi as a purely virtual particle, but ghosts, the ghost people have published their results, and the results are anything, they don't have the lower bound. They just have half line. But what is the origin of their result? You know, the origin of their result is that because the problem that people from high energy physics don't appreciate in cosmology is that they think that if something is heavy, you can neglect it at low energies. This is very heavy, and the predictions for cosmology are sort of low energies because they're super horizon. But in cosmology, you cannot. And just think about the Bunch-Davies vacuum condition, which is about the opposite limit, which is the ultraviolet. And many people do not want to accept that condition so easily, and maybe they are right, because you are imposing a condition about a region you will never reach. It's just because you have a harmonic oscillator with a constant frequency that you make your bet, and you say, let's hope that there it is the same as here and always. But ghost people have that plus a harmonic oscillator with a constant frequency, but the wrong sign. And they use a Bunch-Davies vacuum condition for that as well. And that is a kind of, I don't find it very justifiable. In my case, you just have the first oscillator, the one with the right sign, because this disappears. Because there, when you reach, well, you have to expand around the theta limit, the projection makes it disappear, really, from the physical spectrum. And that is not the problem. The problem is that once you project there, you have to be sure that it disappears, that it is fake also in the other limit. It has to interpolate. And so basically, normally in cosmology, that's what people always do. They interpolate between UV and IR, and only that gives a prediction. Here you have to add the interpolation to the purely virtual thing, and that gives a limit. But you cannot argue as a high-energy physicist here. And that's why you see this kind of bound would be impossible to obtain from high-energy physics. It would be totally non-perturbable. How can you obtain relations like these in perturbative quantum field theory? In flat space, of course. This is still perturbative, but it is in a non-trivial background. So in the end, behind everything like this, I forgot to mention one important point, is the point is that you cannot, but obvious now that you do not have time ordering. You cannot rely on the physical definition of time for arbitrarily small intervals. It would be too much to think that there is a definition of past, present, and future that holds for arbitrarily small intervals. And since there are many other approaches to quantum gravity that start from that, maybe the connection sooner or later will be worked out. Yeah, one thing I'm not affecting is the background. I forgot to mention it. Yes, another thing that is absolutely coinciding with Starobinsky is the background. I start from that, and only the fluctuations have and this is because y squared doesn't affect the usual solution. It's a lucky situation. Yeah, that is precisely to the difference between sine and hyperbolic sine is related to that, because here, because you do not have a definition of time and ordering of time, you do not have causality, a micro-causality. But you would like to pay this price, not having causality, only for small intervals of time, 1 divided by m chi. M chi, by the way, if it is 10 to the 13 GeV, it means 10 to the minus 36 seconds. If you do not know, you maybe know more than me of this, the shortest intervals of time that have been measured or defined by means of laser pulses are 10 to the minus 17, 18 seconds. So we are very far from there. I'm not claiming that we cannot define time in everyday life. You would like, however, your violation of causality be there only in those scales, and normally this is no problem in flat space. But in curved space, it's precisely the difference between the sine or a hyperbolic sine makes that difference precisely. So if you have a sine, like a sine of m chi times the modulus, this is so strongly oscillating in 10 to the minus 36 seconds that basically it averages this violation to 0 for longer amount of time. If you have hyperbolic sine, I'm not excluding that for mathematical reasons. I'm just saying that you would not have this universe. You have, you can even imagine what. You are a scrambled universe forever without possibilities of forming anything. So that's a kind of phenomenological boundary. You have, but this is only a consequence of the curved background, because you wouldn't see anything like that in high energy physics. So here the problem is not theoretical. I can give you any prediction you wish. I can give you predictions to these corrections. These are the leading orders to 1 part in a million. I've been able to compute them because once you understand the machinery, you can develop a formalism that allows you to do that analytically. It's an expansion in slow row parameter, and if that is small, by the way, I describe inflation as an RG flow with the beta function that has the usual features of the QCD beta function, which is asymptotically de Sitter in this case, and alpha is the slow row parameter in one of the two frames, square root of the one in the other frame. I don't remember if it is the slow row parameter in the Jordan or Einstein frame. Anyway, alpha, if it is a coupling, if you put numbers, is 1 divided by 125. So it's like QED. It's very perturbative. You can compute corrections. And from there, you will see certainly the differences once we will be able to measure them, even the first corrections. So there is a prediction for NT, but NT will be much harder to measure already. There will be different predictions but with the same high energy, the same leading predictions if you have two scalars, for example. So if you have two scalars, well, you can have much different predictions. There are many there's a lot of freedom, but I prove that there is a perturbative region on the specific one where you can apply all these perturbative methods, but you will have them the same leading prediction for R, and only at subleading level you see the difference. I didn't study yet non-Gaussianities like this. It will be the program if I go back to cosmology, because switch from physics, cosmology, and phenomenology. The problem is experimental, and to see the data, the true data among the dirt. Some people tell me that 10 years, 5-10 years, we can see whether this is right or wrong, and some others tell me there is no hope to reach this. I have to be optimistic. Maybe we will make progress and overcome the present obstacles, but not that hard, because basically we have to live only for one number, for one measurement, and here there is an extra parameter. So it's already a lucky situation that the function of this extra parameter doesn't depend too much on it. And so the window is small, because otherwise there would be no prediction. Yeah, this is another part, indeed, of our investigations, because the claim is that you need one for giving sense to gravity, but if there is one, there could be many others. And maybe they are not required to give sense to the fundamental interactions as we know them, but if they are heavy enough, we might not have seen them. By the way, it's not excluded that the Higgs boson is a fake, because of the phenomenological predictions that make the difference between the Higgs, between a fake and non-fake. You cannot exclude that from the data we have about the Higgs boson. You can exclude that for Z boson, for Ws. For example, when you have a peak as neat as the Z1, you can be sure it is a physical particle, but if it were fake, you would not have a neat peak, you would have something different. And with the peak of the Higgs boson is still too dirty from the experimental apparatus. It's enough to say that there is something, but it's not enough to say what it is. I do not want to claim that Higgs boson is fake. I just want to say that it could be still to be settled. But other things that are so phenomenological, with some groups in Tallinn, we have explored possibilities, more fashionable possibilities that might explain the discrepancy of the G-2. I don't think it's certain that there is a discrepancy, but just in case something. We have also considered the possibility to use these things for dark matter. Preliminary conclusion is there is no possibility to use this for dark matter. I don't think, because they are fake. They are not dark. They are fake, and they mediate. I don't know much about dark matter, but the things we have explored preliminary again suggest to me that it's hopeless. And then there are other situations where you do not see much differences from the usual thing. For example, black holes. Anything that is static, that doesn't involve time, will not show the difference between any prescription, I epsilon, non-I epsilon, fake or non-fake. So there you have to work more. So that's why this cosmological thing came really good, because of the background with more challenges, but time dependence is crucial to see these things.